you have any opening statements?
With the compressor running?
Yeah.
No. Opening statements is I'm smiling because I know it's fixed. We are back. This car is fixed. Here's an image my brother sent me yesterday. He put the new sensor in, and this image you're looking at, look at the difference in peak voltage. Now he measured this sync notch here, and it's showing a peak number 1 of 6 volts at the peak right there. Number 2 is showing a peak of 3.96. So huge difference in amplitude. I don't know if that was running or cranking, but that is way more voltage than what we saw. So we're gonna do a running one first, and then I need to simulate the no crank or no start condition through like a clear flood crank or something, so we can get a cranking amplitude of this sensor, okay? And remember, again, motion magnet conductor, that's how this thing makes voltage. The faster the motion, the higher the voltage. The stronger the magnet, the higher the voltage. And the number of conductors affects voltage too. And then there's one more piece, and it's that air gap. All of that is a factor on this type of sensor. And I'm just really happy we were able to show you guys what a weak one looks like and what symptoms can be. In this case, intermittent no start, intermittent backfiring, intermittent popping through, backfire, pop through the exhaust, same kind of thing. And then intermittently, it would actually stop cranking from incorrect timing. So the computer was not able to recognize those sync notches, messed up the timing, messed up injection pulse. We saw both injection pulse and ignition events dropping out, starting back up, wrong times. These signals need to be coordinated properly for this thing to run properly. That's what we had going on. So let me start this first. We'll see what this looks like. Oh, and by the way, this initial crank will be helpful for us because I'm down at 10 volts. And I told my brother to not charge the battery. I wanted a weak start. Now this might be too weak. I might have to put a charger or a jump pack on this at 10 volts, and I'm probably gonna have to. But let's see what that looks like now. It's 9.9. Let's see if it will start. Ah, hell yeah. Sweet. Let me pause that. We go back, a couple of screens here. Yeah, it's so much better. I mean, look, it fills the screen, Caleb. Like we never, the blue trace, we never had that signal that high. Remember how much higher the green trace was? And this area in here, yeah, this would be initial cranking. We'll just pick one of the lower ones in here. Kind of get a min max. Looks like 0.93, that's cursor 2 up top. The most we had was like 0.4 before, and that was with a good battery charger on it. Yeah, and a valley of cursor 1 is 0. So that's 900 millivolts right there on the smallest waveform I have. Cranking speeds at like 10 volts, 9 volts cranking, not speeds, but voltage. Yeah, I mean, night and day different. And that's cranking. We'll get another cranking capture for you guys, but look at it as the engine started to spool up, as the engine started to crank, and we saw speed increase. Look how much higher this is. Look at that. I mean, it's just burying my scale. So it's not even a good scale to be looking at this on. This is engine running. Pausing that. I don't know that we got a running measurement before, Caleb, did we? Did I actually measure it running? All right, well, we'll measure one of these peaks. Detail repetition, I want both. So with the snap-on scope, you want to set it for detail first, and then use the buffer, pause it, and then zoom out for your repetition. So that's the right way to do these captures. Now I can really zoom in on that capture and take one measurement. I just want a peak to peak with the engine idling. Then I'll raise the RPM too for you guys, and let you see this signal and how it will grow with speed. So cursor 1, this is engine idling, or sorry, cursor 2 is at the peak, positive, and that's showing 3.2 volts. And then cursor 1 is my negative, it's -3. So we have like almost a 6.5 volt peak to peak on this waveform now. That's hugely different. Danner showed me that picture and I was like, score. All right, so let's take a look at this now at a higher RPM. I may actually have to adjust my scales because this is gonna grow so much. Okay, that's your higher RPM. Let's zoom out on the buffer. I may want to change that a bit. Yeah, let me do that capture one more time to really emphasize this. Just gonna do a snap. Really cool looking waveform. Just look at the blue trace before I zoom in. Actually, both traces, blue and green. You see them both increasing drastically in amplitude as I snap the throttle. And that's going to be in this range right here. Right? Snap throttle, RPM increases, amplitude grows as frequency increases, and then amplitude decreases as frequency decreases. That's what you're looking at there. And this is really at a level that's difficult to see and place my cursors. I'm not going to do that. I just want you guys to see the scales to the left that we're showing. We're over 6 volts peak and we're under 6 volts minus. That's a 12 volt peak to peak in this area right now. Let's see if it grows any more than that, if that was the highest. Yeah, it was about 12 volt. About a 12 volt peak to peak. And I don't know that I revved it quite like that before, but I did show that it didn't really grow anymore when we raised the RPM last time. This is where the next day filming is a little bit of a detriment to us because I don't remember exactly the scope settings and specifics on where we were, but watch the RPM or just watch the screen live as I hold the RPM up, and you can see the scaling on the left. Right now it's about a 3 volt plus minus 6 volt peak to peak. And you see it growing with speed. Just look at the scales to the left. And I said too when we started, look how much more amplitude the cam sensor has than the crank sensor. And now they're the same. So pretty cool case study, man. The nice thing too about this, oh, I gotta show the cranking one. But the nice thing too about this is we were able to show cranking voltage even at 10, 9, 8 volts was still enough amplitude with that sensor at that very low cranking speeds for this engine to fire up. So we need to crank one now, right, Caleb? So let's increase our time base for the cranking because it'll be slower, and see if this will give me a clear flood crank. I will try. Just holding my foot on the gas pedal all the way. Nope, no clear flood crank on this one. Okay, so I need it to not start. Ignition 15 amp. Take this one out. We won't have coil firing events. We're not looking at those anyway. Man, is that in there? Why? Okay, cranking it. Good enough. I know from previous measurements when we cranked it over, we were barely hitting 300 millivolts, 400 millivolts peak to peak. You can see the cam and crank signals are the same, relatively speaking, as far as amplitude goes here. And we'll get a measurement of this guy as best we can. So cursor 1 is at the top this time, 1.71 volts, and the minus is 1 volt. So put those together, that's a 2.75 volt peak to peak compared to a 400 millivolt peak to peak. Great case study, great lesson. Weak crank sensor signal. What would you do in this scenario if you didn't have a lab scope? you'd be guessing. You could measure resistance of that sensor and maybe have a resistance difference, but the thing is, the magnets get weak on these, and you can't measure that with an ohm meter. A weak magnet equals a weak signal. So that's one. Another one is the trouble codes that you had for this. There were no codes related to this condition. So we can't plug in our little magic scan tool and read codes and change a part in this case, can we? You need to know your systems, you need to know your designs, you need to know operation, you need to know your fundamentals on this kind of sensor and understand the characteristics of it. This was a great case study for it, and Caleb's gonna pull in some images as in the edits as far as some other case studies we've done showing this scenario in my chapter 21 playlist in my book, which is titled Ignition System Inputs. We cover this variable reluctance sensor in this exact issue. It's nice to see it again. It's been a long time since I've seen one. The symptoms of this were pretty awesome. Backfiring through the exhaust, engine cranking where it would almost stop, timing related. What would someone do on a guesswork without a lab scope? Or maybe you even measured sensor resistance if you even knew to do that, and it measured fine. What are you gonna do? What part are you gonna change here? I could see a timing belt being thrown on this car. I could see ignition coils being thrown on this car. You just see it all the time. Parts changes cost you. If the customer, you guys are watching me, your parts changing mentality where you're gonna read codes, change a part, will cost you way, way more in this scenario than what we found here. This is a standard diagnostic charge and a crank sensor. Done, fixed. Pretty cool stuff. Guys, thank you so much for joining me. Hope you guys learned something from this one. If you want more training, I know I say this all the time, but this is what we do. We have training on my website, ScannerDanner.com. You can join my classes. I'm teaching page for page through the book, lessons that I mentioned through this video, and you guys can learn this stuff remotely. I hope to see you there. It's still super cheap. It's $11 a month right now for over 400 hours of training. 400 hours. We have like 520 videos on the site right now and counting. Hope to see you guys there. Thank you. See you next time. You guys left off talking about ignition inputs. Why don't you guys turn to chapter 21. Questions for you guys about the variable reluctance sensor. This is something you covered, right? It's a 2-wire sensor, makes its own voltage. Any questions on that? What do we need to make a voltage? Using, I'll help you a little bit, using magnetism. What do we need? Motion magnet conductor. Those are the 3 things we need to make voltage with magnetism. I need a conductor, I need a magnet, and I need to move the magnetic field across the conductor, or I need to take the conductor and move it across the magnet, right? We need that to create voltage. That's what we're doing. And we use that as an input for a computer. So that's what this image shows you, right? As a tooth is moving into this, we're stretching, moving the magnetic field, we're creating voltage. Does this sound familiar, some of the stuff so far? Another characteristic of this sensor is it produces low voltage at low speeds, and the higher speeds the voltage rises. It's just a characteristic. It isn't intended to do anything, it's just a characteristic, but it's one we have to pay attention to. Cranking speeds, this was a car I took this picture from, cranking speeds of a VRS, there's your signal. This next picture is idle speed, and then the next one after that is 2000 RPM. So what happened with the signal? It got faster, of course, because the engine's spinning faster, but it also grew, didn't it? So where we're going, this first case study, we're gonna really focus on the amplitude, the min-max voltage of this signal. It's really important. Remember, the characteristics of this sensor is low RPM. It's already gonna be a weak signal, isn't it? Is there a spec that we look for? There's really not. But what we care about, there's an amplitude that we care about, which is what this picture is showing us here. Computers are digital, 0s and 1s, right? Analog signals, AC sine waves, really can't be used directly because it's continuously variable, is how they describe an analog signal. So we need to convert it to digital. So there's a chip in the computer that's looking at this sensor signal, and then what's it doing with it? It's converting it to a digital on-off signal so we can use it for all the transistor controls. Yeah, so the red signal, you see how they correspond directly together? Like every time we get a sine wave, we get a square wave. But there's a point where we have a sine wave but no square wave. These guys right here, these four over here, and then this one over here, they're not being converted. And so what I've always said is the computer is not seeing that signal even though it's there. There is a threshold, a minimum threshold that this has to meet, and that's the number we want to remember. And I've always said this, and I have it in the text, 500 millivolts. 500 millivolts, min-max, is what I want to see from one of these types of sensors at the lowest speed. Do you see in this image how this signal is just barely touching that threshold that I drew there, the cursor, the two cursors, measurement cursors? And you see I have a square wave, right? A corresponding square wave. And then let's just pick one of the higher ones. You see how high this is, right? Notice it's really the same square wave. Now I know the fatness of it is different, but that's only because RPM changed. But what I'm getting at is everything above that line and below that line is essentially a throwaway. So we don't really care about what's above and below it. And that kind of goes back to your question, Ed, is what's the spec? The answer is, I don't know, because every car is different. Every sensor's different. RPMs are different. Air gaps are different. Magnetic fields are different. Conductors are different. Every single one of these is different. So I don't care, but I do care about the minimum. All of this, guys, it's hard, and I heard you say, I like shop better and theory isn't my thing, right? It's hard sitting in here and trying to focus on this stuff because you guys don't have that perspective yet of when you need it. That's the hard part. The hard part sitting in here and getting all this theory is you can't connect the dots very well. And what will happen, and every technician experiences this, when you leave here and you start touching these cars every day, then you start remembering things that Mr. Westlick was talking about, right? Oh, he mentioned that, and oh, I'm seeing it now. Oh, now it makes sense. And then you kind of, are a little angry with yourself that maybe you didn't pay attention a little bit more or try to focus a little bit more, and it's tough, I get it. But my goal here with this, I'm gonna show you guys here in a second, this car that had a weak signal that we were able to identify using these same principles, and we just filmed this video just a month or so ago. Using this same principle I've been teaching for years and years and years, applying that same to this car. And so we'll try to make it stick for you guys here, even though we're not in a shop environment, right? We're about to come up on a car that's not starting from a weak crank sensor signal is why we care. And when you look at that signal on a lab scope, you're gonna say, oh, I have a crank signal, so my sensor's gotta be fine because I got a signal. And then the car starts and it runs fine as long as it's running. How do we justify saying my crank sensor is faulty when the car runs perfectly fine when it's running, but it's getting it to start that's the problem? Okay, that's where we're going. A weak signal. What's a characteristic of this sensor? It's already weak to begin with, even before we start messing around with variables, right? This is a known good sensor. It produces weak voltage at low speeds because of the characteristics of the sensor. When we do the Hall effect next after break, the Hall effect is an on-off square wave that the amplitude never changes. It's a much better low speed triggering device. Do you understand why? Because a Hall effect's digital right from the get-go. It doesn't matter how slow I move the crank, that thing's gonna be zeros and ones, right? 0.5, 0.12, 0.1 I used in reference to binary coding, not voltage levels. Much better low speed triggering device, which is why all of your ABS wheel speed sensors now are using digital pickups. Well, we'll get to it. I called it a two-wire Hall effect. It's really not. They're called magneto-resistive pickups, and technical fancy words, but it's a two-wire that's a digital signal. Why did they go to that over these variable reluctance sensors? Because it's not a good signal just characteristically based on its construction. It's just not. So Hall effects. We left off talking about variable reluctance sensors, which is a 2-wire sensor makes its own voltage, right? This is chapter 21, still we're in. So we're now would be starting, just to give you guys the right page here, chapter 21, page 20. So it would be 21-10 for you guys is kind of where we're at. And I thought rather than reading this page to you, I'll just start with kind of drawing a internal of a Hall effect, and then just kind of plugging that in, review the variable reluctance sensor one that we just talked about. So the 2-wire variable reluctance sensor is low speed, weak signal, faster speed, right? It grows, right? That's the characteristics of the sensor we just talked about. The characteristics of this new sensor, which is a Hall effect, it's digital signal, on off. It does not make its own voltage. It manipulates voltage, and it's a high-low signal all the time. And so the comparison between the two would be a square wave here and then a more frequent square wave, right? These should all be the same. My drawing is horrible. And then it slows back down. Maybe better, let's do it like this. Here's a slow signal, and then it's gonna get more frequent and faster, right? The point being, let's say, right, this is high and this is low. The height of this is not changing. The valley of this is not changing, unlike the sensor we just talked about. So this is a better, more reliable, low-speed triggering device.
Does it still carry the same 500? No.
It does not. Good question. Face value, no, it does not, because our signal is the same amplitude all the time. Now, amplitude does matter, but not the same way. So when we talked about the threshold, we're talking about like what is above and below that line. It needs to cross that line to be seen. All right, so with a Hall effect, we have a square wave. It's either on or off. However, similarly, there is a threshold that this needs to cross to also be seen. I want to say that it's halfway. That threshold, it needs to cross above that line, that threshold right there, right, that little dot, and it needs to cross below that. So to trigger whatever it's triggering inside of that module. So there is similarly a threshold, but it's not like a min-max. It's a one line. It's got to cross that line this direction, and it's got to cross that line this direction to trigger your zeros and one communication language inside the computer. The heart and soul of a Hall effect is a transistor, right? And then you'd have generic picture here, but this will be a permanent magnet. And so then you'd have a shield that would ride in between these, like a trigger wheel, right? It would shield that. But it doesn't matter if I'm turning this crankshaft by hand. I could have the key on and turn the crankshaft by hand, and I could make that Hall effect signal fix high. So then I take the crank and I just nudge it with a ratchet and move that window, like this window right here, just inside of that, and then I take that signal and it pulls low. So it's an extremely reliable, low speed triggering device, right? I think that's why a lot of manufacturers move to the Hall effects over the VRS pickups. I don't know, not really that important, but it's different. Like characteristically, it's different. But there is a threshold, and let's say that in my example, this is 0 volts and this is 5 volts, and you have some type of switch malfunction where it's not going that high, and let's say our square wave looks like this. Maybe it's like 0 and the peak is 2. That is not going to be seen, even though it's there. Like the computer's not seeing it because it's not crossing that threshold. What's the threshold? Every one of these are different. I have a case study on it was an Acadia. It was one of the cars here. We had a rear wiper motor, computer controlled. The switch up front was a 0-12 on-off push button switch. So essentially it's the same thing we're talking about here. There's a threshold, right? We can call this on and call that off, right? Somewhere in the midpoint of that. It was 6 volts, but I actually put in a variable resistor in that circuit to see where that threshold was, where the computer would recognize the switch and turn the rear wiper on. It was exactly 6 volts on a 0-12 volt switch. So it's like 12 volts is on, 0 volts is off. Technically that's not accurate. It's 6 volts is on and 5.9 volts is off. You guys with me on that? Like as far as crossing a threshold. So it's there with everything. And that's why I was like, initially I said no. And then I thought about that. I'm like, wait a minute. There is a comparison here. But I didn't plan on talking about it, but it's there. That's chapter 2 material. Switch inputs, that's where we are with Hall effects. It's a switch input. A transistor we talked about a little bit last segment, and we said that the base, so I'll just draw this as our ignition coil that we were talking about earlier. To make this coil work, we need current flow, right? To have current flow, we needed to turn the base of the transistor on. We turn this guy on, and then it allows flow through, right, through the coil winding, through the transistor to ground. Turn this transistor off, turn the base off, and we lose that path, and it just basically stops right there. That's what's in a Hall effect sensor. There is a transistor that's switching on and off. What switches it? What switches this guy down here, the base of the transistor? What's triggering that is this magnet. The magnet is. What's inside of here is this guy. Who made that? Aliens made that, okay? And when a magnet contacts that guy, it generates voltage and it switches the transistor on. The part that we have to worry about as technicians is the signal to the computer. And so it's not quite like this. This is chapter 21. 21-13 is where you'll find that picture. There's 2 different types, 27 and 28. So we have pull up and pull down circuits. Okay, this is the part that's important. And unfortunately, this is the part that like no one teaches you on. Like when you're troubleshooting in the field, to know what style of Hall effect you have, whether it be pull up or pull down, is absolutely critical. It's absolutely critical. All right, so I want to cover this picture with you, but to make it even more simple first, because it applies, I want you to jump to chapter 2, and I want to talk about pull down and pull up circuits.